Welcome to our introduction to bioenergetics and oxidative phosphorylation, the core of how biologic systems transfer and utilize energy. Bioenergetics describes the fundamental transfer and utilization of energy within biologic systems, relying on key thermodynamic principles. By understanding the initial and final energy states, we can predict whether a chemical process is energetically feasible. It is crucial to distinguish between thermodynamics, which predicts if a process is possible, and kinetics, which measures how fast it occurs. To understand bioenergetics, we look at the thermodynamic quantities that govern chemical reactions. Enthalpy, or heat content, and entropy, the measure of randomness, are the two primary factors changing during a reaction. Free energy, represented as G, combines enthalpy and entropy mathematically to predict the direction of a spontaneous reaction. The change in free energy, delta G, provides the vital energetic feasibility measure for any given chemical reaction. We must differentiate between delta G, which is variable based on concentration, and standard free energy change, delta G degree, a constant at defined conditions. A negative delta G signifies an exergonic spontaneous reaction, while a positive delta G indicates an endergonic process requiring energy input. When delta G reaches zero, the system is in equilibrium, meaning no further net chemical change occurs. Several factors dictate the direction in which a chemical reaction proceeds. The actual delta G of a reaction depends heavily on the specific concentrations of the reactants and products present. We calculate delta G by accounting for standard conditions, the gas constant, temperature, and current concentrations. The free energy of a forward reaction is equal in magnitude but opposite in sign to that of its reverse reaction. The relationship between standard free energy change and the equilibrium constant allows us to analyze reactions at standard concentrations. By knowing the equilibrium constant, Keck, we can predict the spontaneous direction of a reaction. Free energy changes are additive, meaning we can sum them across sequences of consecutive reactions. Energy coupling allows biochemical pathways to proceed by linking favorable and unfavorable reactions. Favorable processes can drive unfavorable ones as long as the total pathway delta G remains negative. We can visualize this through a mechanical model, where a favorable gear movement drives an energetically unfavorable process. In conclusion, bioenergetics provides the essential predictive framework for understanding the feasibility of life's complex chemical reactions. Remember, delta G predicts feasibility, concentrations dictate actual direction, and energy coupling allows life to overcome unfavorable thermodynamics.